Hi guys, it's Mr. Krieger. Today we're going to do a regression review. Make sure you print up the lesson. And before we get started with the actual lesson, I wanted to go over some basic concepts that you should keep in mind when you're dealing with regression. First of all, when you're describing a regression line, there are three descriptors you have to use. Direction would be positive or negative. If the regression line is going upwards or downwards, that's direction. Form is it linear or nonlinear? And finally, strength is how good is the fit with the regression line to the data. If the points are all over the place, but it seems to be going in one direction, it has weak strength. But if the points are very close to the line, then it'll be strong. Okay. R, the correlation coefficient, will indicate direction and strength. Positive will be a positive direction. Negative will be a negative direction. And the closer R is to 1 or -1, the stronger the relationship is. And the closer it is to 0, the weaker it is. Now, R doesn't tell you the form, but let's jump to here for a second. The residual plot, when you take a look at the residual plot, if the points are scattered nicely above and below the residual plot, you could tell that the data would be linear, or that the model fits, okay? Now there's another thing related to R. It's R squared, literally when you square this value. R squared is the coefficient of determination, and that will tell you the percentage of variation caused by the explanatory variable. So we'll take a look at some examples after, but you know, sometimes there's multiple things that affect the outcome. And this number will tell you the amount of the effect of the one variable we're using as the explanatory variable on the response variable, okay? And now when you write a regression equation, and especially now, you know, sometimes you would see it as, and I'm going to write it over here, sometimes you'll see it as like y hat, you need the hat, equals, let's say, ax plus b, or y hat equals a plus bx. Sometimes you'll see it like that when you run the regression on the calculator, where in this case, the a is the slope, here b is the slope, it's irrelevant. But really, I don't want you writing the regression equations like this. The way you should be writing your regression equations are this way. The y hat is going to be your predicted response variable, and be specific to talk about what that variable is. That's going to give you context. Equals, now depending on how you're writing it, I'm going to do it this way, slope times the explanatory variable. Now, the explanatory variable is going to be, put the specific context in. What is the name of that explanatory variable? I'll show you an example when we do the problems, okay? The slope is the number that you'll be given, or that you find from doing the regression, and then plus the y-intercept, okay? So let's take a look at the first problem. Commercial airlines need to know the operating costs per hour of flights for each plane in their fleet. In a study of the relationship between operating costs per hour and number of passenger seats, investigators computed the regression of operating costs per hour on the number of passenger seats. The 12 sample aircraft used in the study included planes with as few as 216 passenger seats, and with planes that have as many as 410 passenger seats. Operating costs per hour ranged between $3,600 and $7,800. Some computer output from the regression analysis of this data is shown below. Here you could see they put the least square regression line in there. They gave you this output here. See, you don't even need to run the regression. They gave you everything you need in this table. Now, we never got to learn these things. Don't worry about it. You'll never need to know it, or this. The things that you're going to need to know, you're going to need to know the stuff here and this. That's really all you're going to need to know. Now, when it says constant, that number is your y-intercept. And seats, that's your explanatory variable, and that's your slope. Okay? So the first thing they want us to do is they want us to write the equation of the least squares regression line that defines the relationship between operating cost per hour and the number of passenger seats on the plane. All right? So here, like I was telling you, don't put y hat. write down predicted cost. So here's the equation. Predicted cost, the word predicted, and then the variable. The variable is cost. That's the cost is right here. That's the y variable. Is equal to, now we're going to put in the y-intercept first, but it doesn't matter. And the y-intercept, as I told you, is that number right there, 1136, plus this number, which is the slope, 14.673 times the number of seats. So you're not going to use y hat and x. You're going to use cost, or predicted cost, and a number of seats, and you should definitely have that word there, predicted cost, okay? Don't write anything with a y hat or an x. Put in the names of the variables, okay? So here's your regression line. Okay, so the correlation, what is the value of the correlation coefficient for operating cost per hour and the number of passenger seats in the plane? Interpret this correlation. So it wants to know the correlation coefficient that relates passenger seats to cost per hour, and that's where we're going to use the r squared. Now, r squared is not the correlation coefficient. The correlation coefficient is r. So we're going to have to take the square root of that number, basically the square root of 0.57. Now, the square root of 0.57 is 0.755. Now, this number is the correlation coefficient, okay? And now it asks us to interpret what this means, right? So what this means is that there's a pretty strong, let's say, pretty strong, positive, and linear, this data, after all, is linear relationship between, and you want to use your context here, between number of seats on the passenger plane, number of seats, all right, and the operating cost. Okay, and that explains what R is. Okay, now for part C, I don't even know if I have to write anything here, but if I do, I'll write it on top. Suppose that you want to describe the relationship between operating cost per hour and the number of passenger seats on the plane for planes only in the range of 250 to 350 seats. Does the line shown here in the scatter plot still provide the best description of the data in this range? Why or why not? So we're talking between 250 and 350. So basically, we're only going to look at this as if these points don't exist, right? Well, if these points don't exist, this doesn't seem to fit that data well. It actually looks like it's more of a negative relationship in that area. Probably should have been that way a little bit more. So I would say no. For passenger airplanes in this range, there seems to be a negative relationship between the number of seats and the cost per hour, okay? All right, so that's the first question. Let's take a look at the next question. We might have done this question in class already, but it has a lot of good parts to it, so we'll take a look at it again. All right, so let's see what it says. The Great Plains Railroad is interested in studying how fuel consumption is related to the number of rail cars for its trains on a certain route between Oklahoma City and Omaha. Here's a random sample of 10 trains and the number of rail cars and the fuel consumption, right? Here's a scatter plot. Here's the residual plot, right? And they gave the data in this section right here. I'm going to get a piece of paper out because there's going to be no room to work here. And it says, is a linear model appropriate for modeling these data? Clearly explain your reasoning. If they're asking you if a linear model is appropriate, look at the residuals. The residuals will tell you whether or not the linear model is good. And when the points are scattered about this line, some above and some below with no particular pattern, then it means that a linear relationship is appropriate. In this case, that would be the argument. Okay, now the next question is, suppose the fuel consumption cost is $25 per unit. Give a point estimate, a single value, for the change in the average cost of fuel per mile for each additional for each additional railway car attached to a train. Show your work. So here, we know after each additional railroad car, right, adds this amount, I'm going to put it over here, 2.1495. That's the additional, fuel consumption for one additional, and what I should say is additional fuel consumption. This number is not a precise number. This is the predicted additional fuel consumption if you add one railway car. So we're going to be consuming whatever, let's say it's 2 gallons of gas, whatever kind of fuel the car is using, that's how much extra fuel it's using. Now, it costs $25 per unit of fuel. So what you're going to need to do to find the cost is take the additional amount of fuel that one railway car will create and times it by $25, and that's going to give you a predicted value. It's not the actual value, because again, this is based on a regression model, which will give you some reasonable estimate, but it's not going to be the exact value, because one train to another might have some variation, but it's going to cost an extra $53.75 for every additional train car you add to the train. All right. Interpret the value of r squared in the context of this problem. There's your r squared. Your r squared is like 0.967 or 96.7%. Now, again, here's the thing that you keep in mind. This is called the coefficient of determination. There are sometimes multiple factors that cause the response variable to react. It seems like the majority of what causes additional fuel cost for a train is the number of railway cars you're adding. So for each additional railway car, that explains 96.7% of the variation in fuel consumption. So, okay? You actually probably want to say there is it explains 96.7% of a linear relationship to the fuel consumption of the car. Okay? And part D, would it be reasonable to use a fitted regression equation to predict the fuel consumption for a train on the route that has 65 railroad cars? Okay? Now, if you take a look, we have a minimum of 20 railroad cars on a train and up to about 50. 65 is out of that range. And we've talked about this when you try to make predictions outside the range, that you run into some difficult territory there, and chances are that's not going to be accurate. So you would say, no, we cannot tell because 65 cars is outside the range. You could also mention that this would be an example of extrapolation, and it's not a valid way to make a prediction. Okay, so you don't want. So this is a case of I can't spell. I'll put it over here. Extrapolation. So extrapolation we don't want to use in regression because it's not. It sometimes doesn't give us good results. All right, last problem. It's a 2-page problem, so the information's on here, but some of the questions are on the next page. But we'll just start by reading the problem first. Okay, so here's what we have. A student measured heights and arm spans, rounded to the nearest inch, of each person in a random sample of 12 seniors at a high school. A scatter plot of arm span versus height for the 12 seniors is shown. So height is on this axis, arm span is on this axis. Based on the scatter plot, describe the relationship between arm span and height for the sample of 12 seniors. So look, I would say it's pretty linear, right? I'd say the form is pretty linear. I would say that that in terms of the strength, it's not that strong because I would say it's moderate, because even though the points are generally going up, they're spread pretty far out. So I would say it's a moderate linear relationship. And in terms of the direction, it's positive. So in this particular case, you want to say, let's see, the relationship between, and here's where your context is, between arm span and height appears to have a positive, moderate linear relationship. If you want to say it even better, you might want to say something, the relationship, let me see, yeah, maybe it's just the relationship between arm span, yeah, that's fine, same thing, all right? So let's take a look at the next part of the problem. It says, let x represent height in inches and y represent arm span, so height is here and arm span is here. Two scatter plots of the same data are shown below. This graph shows the data with the least square regression line, and they give you the regression line here. And this graph shows you the data with the line y equals x. So this line here is y equals x, nothing special, right? Let's go grab the next sheet. Okay, so now the question is, the criteria described in the table below can be used to classify people into one of three body shape categories: square shape, tall rectangle shape, or short rectangle shape. The square shape, arm span is equal to height. Tall rectangle, arm span is less than height, and short rectangle, arm span is greater than height. So the first part of B is, for which graph, 1 or 2, is the line helpful in classifying the student's body shape as square, tall rectangle, or short rectangle? Explain. So we have to pick from one of these models. This model actually shows you, and by the way, these 3 points are actually on the line. This model shows you points on this line, height is equal to arm span. Points below this line, height is greater than arm span, and the opposite's true for points above this line where arm span is greater than height. So you would want to make the argument for BI that use graph 2. Bear with me 1 second. Okay, use graph 2 to show these categories, since y equals x will show when arm span is equal to height. Okay? Now it says complete the table of classifications for the 12 seniors. Now I have some extra dots on my thing because it bled through. But let's talk about the square. The square is where arm span is equal to height. So that's these 3 dots here. So that has a frequency of 3. For the tall rectangle, let me just get, because it's hard to read my thing now. Bear with me 1 second. Yeah, here we go. For the tall rectangle, arm span is less than height. Arm span is less than height over here. Okay, so we had 1, 2, 3, 4 dots there. Frequency 4, and short rectangle are these, don't ignore that dot that I made. It's 1, 2, 3, 4, 5. The short rectangle, the arm span is greater than height, and there are 5 of those. Okay, using the best model for prediction, calculate the predicted arm span for a senior with a height of 61 inches. Now they gave us the formula or the regression line to do that. They didn't put context in here because they told you what everything was representing. Now, if you want to figure out a height of 61 inches where x represents height, you would just plug in the height of 61, and you get your y hat, which will equal 62.05 inches. And I would actually literally write out the predicted arm span. Hold on 1 second. The predicted arm span is 62.05 inches. Okay, your homework is the rest of this handout, and will be due next Tuesday.